In this video, we will be preparing an input file for two-photon absorption calculations. This is a specific case for degenerate two-photon absorption, which is the more popular calculations compared to the non-degenerate one. But in any case, you can do both degenerate and non-degenerate two-photon absorption in TURBOMOLE using TD-DFT and RICC2. One thing to keep in mind is that we've already established the RICC2 two-photon absorption input file, and in this video we will be doing a TD-DFT two-photon absorption input file. There are two ways to do this. The first one is using the terminal defined in TURBOMOLE, and the second one is using the GUI. But in the GUI itself, you will have to do some changes to the control file or your input file, and you will not be able to run it using the GUI, because if you do so, it will change the calculations to vertical excitations. And if you use the second method by using the GUI, you would have to keep in mind that you have to follow what you're doing in terms of removing some of the commands in the input file. So let's start with our bash RC. And then, so we've established the environment. We want to go to our input file. We want to go where the coordinates are. They've already been converted to TURBOMOLE coordinate file. And we're going to use the same test we've used before for the GFP anionic chromophore in this case. I do have some files here. I'm just going to remove them so that we can proceed with the two-photon absorption input file for TD-DFT calculations. So we're going to start with the define itself. And as usual, I don't really just put in anything, so I just skip all of this and start by loading the coordinates. You can see the atoms here, they're equal to 0, symmetry is equal to C1. Now I know that the symmetry herein, I want to be consistent with my calculations, for example, for RICC2 and TD-DFT, so the symmetry is C1 in this case, so we're neglecting the symmetry, but I know that the symmetry of the molecule could be CS. If I want to do the calculations for CS, I can just switch it to SYCS, and the symmetry is CS right now. Now, if it's not really CS, for example, if you're not really sure, then in any case, using the GUI itself will give you the symmetry. It will auto-detect it. If you're not really sure about what's happening, just make sure when you change the symmetry that the number of atoms doesn't change, because if it doubles, then this means that this is not the symmetry. It is not the symmetrized molecule that you're actually looking for, most likely. So make sure that you follow whatever you do when you use define or when you use the GUI. Just make sure that you understand what happens in the input file. So now that we've loaded the coordinates, we will just end this menu, and then we will jump into the basis set. So I will use the OGCCPVDZ, and I'll use it for all atoms. So I'm just writing B to assign the atomic basis sets for all atoms in the coordinate file. And I'm going to use the OGCCPVDZ basis set. So if you want to use another basis set, for example, DEF2 SVP, you would have to use DEF2. You would have to write it exactly like it is in the manual, like it is in TURBOMOLE, which is the known way for theoreticians. It's DEF2 SVP, all capital, and for other basis sets as well. So you just make sure that you write it properly. And if you don't, I don't think it's going to recognize it. So make sure you do that. Now that we've assigned the basis set, and we can see here in for the atomic attribute definition menu, we have the atoms, we have the base, or the basis sets. And right now we're done with the basis sets, and we want to print the molecular orbitals by using Huckel guess. So we're printing the molecular orbitals from the menu by just writing the command EHT. And I want them all to be default. And I know that the charge, just like in a previous video for GFP anionic chromophore, it's an anionic chromophore, so the charge is -1. I already know that, and it will be a singlet when I specify that, and it's seen. We can see that from the occupancy. I just want to keep the occupancy as it is, and then because I'm using CS symmetry just by following the group theory, CS has two irreducible representations, the A prime and A double prime, and each one of them has different molecular orbitals. Now you can specify that you want to do the calculations for different states, for both irreducible representations, or you can select only one. It depends on what you want to do. In the case in my calculations are in, I just want to do A prime. That's what I'm interested in. I want to do I'm interested in doing one excited state for A prime. This is something we'll talk about just in the next menu, not this menu. So right now we want to just know what functional we're going to use. So we want to use DFT. And for DFT, it says that here DFT is not used. So DFT is not used in the functional is BP. This is the default one given in TurboMole, and the grid size is M3. Now for the functional, we want to change it. I want to do can be 3-lib. Make sure that you write the functionals properly as well, like I have the dash in between the cam and B3lib. So the functional I want can be 3-lib. And for the grid size, I want it to be, for two-photon absorption, I want a larger grid size of M4. Okay, so we can see the functional changed when I wrote the first func. And the grid, when I changed it to M4, it changed, the grid size changed to M4. But still, we don't have DFT switched on, so we have to switch it and just write on in this menu to switch on DFT, and it says here DFT is switched on. We terminate this menu, so we've been able to do DFT for now. We have the DFT calculations, and we can see herein, but we don't have TD-DFT yet because we're only doing, so we can see the basis set we've selected, the molecular orbitals are printed out. We have A prime, A double prime for these molecular orbitals of 49. And this something, and then you have the functional here, the functional can be 3-lib and the grid size is M4. So we don't have TD-DFT yet. We don't have excited state calculations yet. So what do? We go to the excited state and response options, and we want to use response for sure. And for two-photon absorption, we use nonlinear response. So we want to just use EX. And I know that my calculations, you'd want to make sure that you know what type of calculations you're doing. So if you're doing singlet excited states, or singlet excitations, you will use RPAS. If you want to do singlet excitations with CI singles, but this is not really the case of singlet, with CI singles, then you would have to select CISS. But this is not really the case for TD-DFT. We want to use TD-DFT. We want to stick with TD-DFT. So we have TD-DFT here, or we have so we have RPAS or we have RPAT. These are the options for TD-DFT that we're looking for. And I know for my calculations, I'm interested in singlet excitations. And in singlet excitations, I have to select RPAS. If I'm interested in triplet excitations, I would select, for TD-DFT, I would select RPAT. So it's the singlets and triplets. That's what it really stands for. So right now it says here it was off when I clicked RPAS. I want to do singlet excitations, which is what we're interested in. For RPAS, it goes to on. The status is on. Oh, sorry. So right now I want to quit this menu. And when I do that, it prints out a couple of things for the molecular orbitals. And then for the non-frozen orbitals and the non-frozen occupied orbitals of 49. And then we have the character table herein, basically, just looking at it, we can get the number of states for A prime and A double prime. As I mentioned before, I'm interested in A prime. And this is, right now, you want to mention how many number of, so it says here, select the irreducible representation number of states as well. So in A prime, I want, for example, 2 states, 2 first excited states. And if we're interested in 3, we can just write 3. If we're interested in 2, we put 2, 1, 1, etc. So let's say I'm interested in 3, for example. I would write A prime 3. And it says here that the selected for A prime, there's 3 excited states. Okay, that's good. We print out. And then it talks about the recommended memory. I'm not interested in changing the memory. You can change it if you feel that you need to. Then we'll leave. Yes. And that would be it for the two-photon for now. Now, what we've done, if you go to the control file, what we have done so far is just doing, technically speaking, this is singlet excitations, but this is if you do the calculations of this one, this is singlet excitations. But this is not really the case of singlet excitations. This is not really the case of singlet excitations. This is 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 singlet excita what will happen is that you will get, I believe, vertical excitations, but you will not get two-photon absorption. So the one thing you need to do in the SCF and stab here, just write a space and just write 2-photon. And when you do the 2-photon, no space here. So when you do the 2-photon, so it's SCF in stab 2-photon RPAS, it will, when you run the calculations using the terminal, you will get 2-photon absorption, but you will have to use the terminal to run the calculations. If you do not, then it will, if you use the GUI, it will jump back and just run it as if it were vertical excitations. Now this ends the first way of doing the calculations you're in. Sorry, it's preparing the input, not doing the calculations, preparing the input for 2-photon absorption. Now the other way is just using the GUI to generate vertical excitations, and from there you can just go to the control file, remove a number of commands, and just change the SCF in stab. So just go, for example, we have this file here in, and in this file, what I want to do, I want to do a new job. We import geometry. I want the GFBA. And let's say, so you see here, the symmetry is C1, auto detect symmetry, CS. You can select whatever basis set you want, but you have to know you are limited. You don't have all basis sets you in. So if you want OGCT, PBDZ, double, triple zeta, with or without diffuse, you will not be able to get them here. You would have to change them. And that's actually relatively easy. So I'm just going to leave this as it is right now, and I'll show you how to change it later on. You go to continue. The molecular charge, I already know it's -1. And we generate the molecular orbitals, and we have fully occupied 49 orbitals, and the multiplicity is singlet. So we have molecular charge -1, and its multiplicity is 1. We go to continue. We're not interested in using RI for DFT. You can change the functional to whatever you want. Let's say, for example, you want to use hybrid PBE, the grid size M4. You can add dispersion if you want to, and you go to continue. You do single point, for example, vertical excitations. We want to select, you can just do all irreducible representations, it's up to you, or you can do just select irreducible representations, but it doesn't seem that I can actually select one from here specifically. So I'm just going to do all irreducible representations, and this is something that can be changed later on. I'll show you in just a minute. So for all irreducible representations, I want 2 excited states. You can save the file. It will save on your projects file for TurboMOLE, and that's it. So you've got the file itself, job SP5. This is the file that we've generated, the SP file. The SP5 is the one we've generated using TurboMOLE. Now, there's a couple of things that we want to look into. So the first one is we have functional PBE, the hybrid PBE, and the grid size is M4. It says here SOES for the number of excited states for irreducible representations. They're all under 2. So this all means that we're it's going to do the computations for all irreducible representations in the whatever point group you have, whatever symmetrized you have or none. If the symmetry is neglected, it will simply be just A, and the excited state depends on what you have. And if it's not, then it just using the GUI, it will write down as all, and we have 2 excited states. Now you can remove this because I'm interested in doing 2-photon absorption, but not really looking into this. I don't like having a subtitle. It's fine by me. You can keep it if you want it. And here in the SCF ends tab RPAS, we're doing single excitation. Just leave a space, and then you write 2-photon. 2-photon, no spaces, and everything looks okay. So there's a couple of things that I want to mention here that you've read that you want to change it into 2-photon absorption, right? So you want to keep in mind a couple of things. Do you want to do A prime and A double prime for the CES calculations or not? Let's say you want to make some changes. The easiest way that I find making changes is if I have an already input file that I already made for Two-Photon or whatever, something else. So for example, SOES here, let's compare this. On the right, we have the GUI generated input file. On the left, we have the terminal generated input file using define. SCF instab is Two-Photon. It's the same thing. So we're going to do Two-Photon absorption here in. And we have the symmetry CS for both. For the atoms, you can see that the way it's writing it, OXCCPVDZ, whatever it's here. But here for the atoms herein, it specifies each atom. This is how the GUI is doing it. You can basically just change it like this, and you can write down the basis set, whatever basis set you want. For example, you want to do CCPVTZ, you can just change it like that. But when you change it like this, you have to keep in mind that you've already printed out the molecular orbitals, so just remove them. And when you remove them, you would also need to delete them from your file, because when you do the calculations, the first thing you will do is a DSCF. When you do an SCF calculations, it will use the basis set CCPVTZ. When you do that, what happens is that it will generate the molecular orbitals as CCPVTZ. But keep in mind that you already have basis sets here that are written out for def SVP, which is something that you've used for your molecule. Okay, so you can change the basis set easily. It's not really a problem. But in order to change this, you can either if you have an already generated CCPVTZ basis sets or something else. Okay, so what I'm gonna do, I'm gonna switch it back to OXCCPVDZ. Okay, and I already have a basis set file, which is the one that was generated using the terminal file. The terminal, I'm just gonna replace it using the terminal define, and we already have this OXCCPVDZ. Now, it is possible to change the basis set. You can, if you, for example, want to use CCPVTZ herein, you can change it into CCPVTZ or whatever basis set you want, and then just make sure you remove the molecular orbitals. And then, if you don't have a generated one, you can go to basis set exchange, see what atoms you have in your systems. Here we have carbon, nitrogen, oxygen, and hydrogen. Hydrogen, and we want it for turbomole. And what do we want? We're interested in finding, for example, CCPVTZ or whatever. You can select whatever basis sets you want. For example, this is CCPVTZ. You get the basis sets in TURBOMOLE and you just copy them. You go to your basis set file and you just copy and paste them. Make sure that that you're using TURBOMOLE basis sets. So you have the basis set, and for example, herein, you will use CCPVTZ. So in this way, we've shown how to do two-photon absorption using the define in the terminal, using also the GUI, and also changing the basis set. And by mean changing the basis set, you can supply external basis sets as well into TURBOMOLE, so you can change them to whatever you want. And that's how you basically just do it. Do two-photon absorption and change the basis set with that. So that's all we have for this video. And of course, just something to keep in mind is whether you want to do for all irreducible representations or not. The define in the GUI does it like this. So we can see here, and I've selected A prime for 3 excited states. You can change it here and just change it, for example, 2 excited states, 1 excited state, whatever you want to do it and how you want to do it. And that's it for today. Thank you.